This is Rosen, Discrete Mathematics and its Applications. We're in section 1.5, and we will talk here about nested quantifiers. We learned about quantifiers in the last section. Now we're going to consider multiple of them. And we'll do the nested quantifiers and order of quantifiers in this short video. Okay, so here we have nested quantifiers necessary to express sentences when you have two variables that you need to bind. Here our example, every real number has an inverse. So there's two numbers, the first number in question and its potential inverse if this is a true statement. And we see here that we're talking about the additive inverse. So for every x, there is a y such that x plus y equals 0. And we have to specify the domains to determine whether this is true. X and y are the real numbers. And this would indeed be a true statement. Let's see, another way to think about this, and the reason that you can consider it nested, is that we can think about for every x, there exists y such that x plus y equals 0. Well, there exists y such that x plus y equals 0 is just a propositional function in x because y is bound by the quantifier. So we can tie that to this q of x here. Okay, so for every x, q of x, where q of x is, there exists y such that p of x plus y equals 0. So one way to think about this is sort of an outer loop and inner loop type of approach, where the first quantifier is the outer loop and the second quantifier is the inner loop. So at each value of x, outer loop value of x, we're going to loop through all the values of y. And if for every x and for every y, p of x, y is true, we will stop if for some pair of x and y, p of x, y is false. Otherwise, we will keep looping through all possible values of y for every value of x. And if for every x and every y, p of x, y is true, the outer loop will end for stepping through each x and will not have found a y for which p of x, y is false. All right, so for every x, there exists y, p of x, y is true. Once again, we'll loop through an outer loop through the values of x, but for every value of x, we'll loop through the values of y. And in this case, if we find a single pair for which it's true, a single y for which the xy pair is true, we can continue on the values of y. So inner loop ends when a pair of x and y is found such that p of x, y is true, and go to the next value of x. On the other hand, if we do not find a y such that p of x, y is true, we terminate and we determine that the proposition is false. So for every x, there exists y, p of x, y is true if we get through all values of x in the outer loop without stopping. And this looping is conceptual if our sets are infinite, but you can still think about it in that way. Okay, the order of the quantifiers will matter, so let's look at some examples. All right, if I have the statement x plus y is equal to y plus x, that's our p of x, y, and our domain is the real numbers, then for every x and every y, p of x, y is the same as for every y and for every x, p of x, y. So it turns out that if you're using two universal quantifiers, you can switch them in front of the propositional function. On the other hand, if we have the statement q of xy is x plus y equals 0, and we're using the real numbers, then for every x there exists y such that q of xy is true. We saw this on the first slide. This is the additive inverse. But if we try to switch the for every x and the exist y in front of the quantifier, it turns out to be false. Because there isn't a y such that for every x, q of xy is true. There's no y such that every x is its additive inverse. So that would make it false. So in general, when the quantifiers are of different types, we cannot switch them. Let's look at some examples. Here are p of xy is x times y equals 0. And is it true that for every x and every y, p of xy? No, it's not. There's many different values that multiply that have a product that is not 0. How about for every x there exists y, p of xy? Well, that's true because if y was 0, then it'll always multiply out to be 0, always have a product of 0. So for every x there is a y such that that statement is true. And what about for there exists x such that for every y, p of xy is true? Yeah, if x is equal to 0, that'll be true. And then there exists x and exists y, p of xy is also going to be true as long as one of them is 0. Okay, so let's look at another one. So x divided by y equals 1 is where the real numbers are a domain. Is it true that for every x, every y, p of xy? No, that's not true. You can have 4 and divided by 2 is not 1. So it's a counterexample. How about for every x there exists y, p of xy? That's going to turn out to be false because consider the value of x equal to 0. Well, there's nothing that divides into 0 and gives 1, so that's going to be false. And is there an x such that for every y you get that ratio to be 1? No. It'll be all different answers. If you loop through all the y's, it won't be a 1. And does there exist x and a y such that their ratios are 1? Sure. Whenever x is equal to y and they're both non-zero, then that'll be 1. And even though these have the same truth value, they both get that truth value for different reasons. There's different reasonings when we have those different quantifiers. Okay, and this has, here we talk about the order of the quantification. You see that whenever the quantifiers are of the same type, you can switch them. So p of xy is true for every pair xy. It doesn't matter which one you consider in the outer loop first. And then for there exists x and exists y, also likewise, it doesn't matter the order of them, whichever one you have in the outer loop. You only have to find one pair of x and y such that p of xy is true and you're done. But if we have for every x there exists y, so for every x there's a y for which p of x is true. When we stop when there is an x such that which p of xy is false for every y. And then there exists y such that there exists x such that for every y, p of xy, that means we've only got to find one x so that it's true for every y. And if there's an x for which there's a y, for every x, if there's a y for which it's false, then it'll be false. But notice we don't consider the alternate ordering of these because those are not the same cases.